Seems to be working. So the next speaker is Marianna Pensky. So she's from the University of Central Florida. And she's going to talk about non-parametric methods for the dynamic stochastic block model and time-dependent graphon.
Yeah, I want to thank the organizers for inviting me here. I heard a lot of very, very nice, very useful talks. And my talk, in a sense, will be kind of complementary to the talks that you heard, because I came from non-parametric statistics. It's my first work concerning any network data. And to a certain extent, it will be also, in a sense, complementary to the Pierre's talk, because he has software for analyzing data, and I will be talking mainly about theoretical tools. And so I will talk about I will start with stochastic block model, and then I will move to the dynamic stochastic block model. To the best of my knowledge, nobody else has done it. I will talk about some existing results, some existing theoretical results on stochastic block model and graphon estimation, because it is impossible to talk about all existing results about the meta, and anyway, if we talk about dynamic networks, the results are well represented at this conference. And what I am going to basically market in this talk, you always try in every talk there is some key component, is not even the results of my theoretical analysis, but much more kind of tools of my theoretical analysis, because although I am going to talk about Bernoulli data, where you have 1 with probability, with some probability, and 0 otherwise, you can easily apply it to data with any other distribution, basically, as long as you have some kind of exponential probability inequalities. And then I will talk about my results and end up with a discussion. So we are going to consider a network which is indirected graph with n nodes. And the stochastic block model usually considers Bernoulli variables, and I'm using slightly unusual notation. So my adjacency matrix here is B not A, because I will need A for different purposes. And you have the matrix which is symmetric, and it has 0 on the diagonal. It actually does not matter what you put on the diagonal, because we are not going to use diagonal at all. And we assume that nodes are grouped into M classes, omega 1 and so omega M, and probability of the connection is entirely determined to which group the nodes I and J belong. So your probability of connection is, if your node I is in group K and node J in group K prime, then this is your probability of connection. And then there are 2 problems associated with this, is estimation matrix lambda, and clustering the nodes into the clusters. I wrote vast literature in the last 6-7 years. It is possible that there is even more old literature, but in statistical inference, this is probably the good estimate of the meta. And this is basically just an example of stochastic block model. So if you order the nodes into the blocks, then these are the probability of connections. This is how it will look like. So associated problem, the problem associated with this is graphon estimation. And graphon can be considered both as the limiting model for the stochastic block model and the generating model. So you can consider a connection of latent random variables. And sometimes these variables are considered uniformly distributed, or they are considered to be independent. Really, in my statistical inference, and I will be talking about statistical inference rather than probabilistic model.
So you're talking about graphons for dense graphs here?
Generally, yeah. It is dense graph. I am not assuming that it is sparse graph, but as I said, what I am trying to present here is methodology. This methodology actually can be easily transformed to the sparse graph, like the things that, say, Klopp, Tsibakov, and Verzelan were doing. And the only reason why I did not is that it stopped being so neat, because you kind of lose adaptivity. You need to, in statistical sense, you need to know you need to have an extra restriction on this sparsity parameter. At least at this point, I don't know how to do it, but this is kind of a methodology that can be extended in different directions. So you can consider it as a first step what I'm trying to do, and then see whether it is useful or not. But as I said, I'm not talking about probabilistic thing. I'm talking about statistical inference, and actually I'm not assuming that anything tends to anything. So n is a fixed number. It can be large, it can be small, n can be 10, or it can be 1,000. You still can use it. And your basically probability matrix is now generated as f xi j, xi I, xi j, sorry, zeta I, zeta j, and zeta I, zeta j just some random variables that are distributed in some way. And obviously this matrix will be identifiable only up to relabeling on variables. And so when we are talking about f, we are talking about equivalence classes of graphons, as it was mentioned many times during this workshop. So you assume that if you have a function mu from 0, 1, which preserves the measure, then f of mu x mu y is the same as f of xy. So we don't care about relabeling. And usual assumption that f has some kind of, I am putting smooth, but what I mean is not necessarily smooth, but it has some structure. So you can have some jumps, but it is not just totally like random noise. And objective, again, to estimate generating function f and matrix lambda. So this is in the static domain, and in our world, everything exists in time, so there is some value in analyzing things in time, and this is what basically I am trying to do here. So now let us move from the stochastic block model to the dynamic stochastic block model. So you again have a network which is indirected graph with n nodes, and at this point I assume that n is fixed. At the end I will show you that technically you can have changing number of nodes at different time points, but at this point let's assume that it is fixed. So we assume that network is observed at L capital time instances on the interval 0, t, and just for simplicity I will scale this interval to 1. I mean, it does not matter. You can replace then 1 over L by t capital over L. I'm not assuming that time is large. I'm assuming that L is that you have certain number of observations. So now you have Bernoulli observations, lambda I, j, L, and again they are zeros on the diagonal, and each adjacency matrix is symmetric, and you have kind of independent sampling of the edges, and but the probabilities, underlying probabilities lambda. So although the samples are independent, the edges actually are not. So you don't have independent structure. And if you think about this, if you think about now that, say, L is growing and lambda ijl is, say, relatively small, then you can consider this. So your sum of Bernoullis, if you aggregate this model, you will have the sum of Bernoulli variables. The sum of Bernoulli is binomial. If your L times lambda ijl goes to some constant, you actually will get your Poisson data. So it is not such a crazy kind of assumption in general. That it is like, think about this. If you even had this in the previous talk, the school children who are interacting, they are not interacting during every small time period when we are observing them, but they are generally interacting. So you will have, even if A is a friend of B, A and B will not interacting during every little time period every time period that we are considering. And again, we consider that there are M classes in which these nodes can be grouped. So G now is a connectivity tensor, and you have probabilities that are determined by the group to which your nodes are belonging. And the number of groups does not need to change, but you can have an empty group at some point if nobody belongs to some group. So there are two problems here, of course, estimation and clustering. And here I am going to consider only estimation of the tensor lambda. Now, why estimation is an important point here is because even when you are looking at clustering, there are two major techniques of clustering, is the spectral clustering and the clustering by non-negative matrix factorization, and all results on the precision of clustering actually depend on the precision of estimation of the tensor of probabilities. Actually, there is no, as far as I know, there are no results for the tensor, but on the precision of the estimation, actually, of the adjacency matrix of the true matrix of probabilities and the spectral norm. So what I'm assuming, and again, that here it is not precise, that probability of connection do not change drastically from one time point to another, and I will elaborate on what I mean by this fact, do not change drastically. So we have some kind of continuity of the probabilities in time. If I have probability of connection, if A and B has probability of connection P at this moment of time, in the next moment of time, unless there is some jump, the probability of connection is very similar. It may change slightly, but it is not exactly very different. And I am not assuming actually the knowledge of the number of classes, so clustering will be into various number of classes. So now the dynamic graphon actually, and this is the place where I don't think I kind of did a very good job, because I just don't know enough about stochastic processes. So I assume that it is generated again by the collection of random variables, and there is time involved in the matrix of probabilities. And of course, it would be good to have L here, but I don't have reliable model, so my graphon is a little more kind of restricted version of the one that could have been. So again, the assumptions here that f is smooth in relatively, that this function f is relatively smooth in T, so the generating function, and that enumeration of nodes does not change in time. So this function mu, which gives the
can identify from one time to
yes. So as soon as
the identifiability problem.
Yes, exactly. So as soon as I fixed each node, the enumeration does not change in time. Otherwise, it will be a royal nightmare every time if we can permute them. So as soon as the nodes are fixed, they are fixed for the whole period of time. And this is actually in every applied problem. As soon as you fix every child in the classroom as 1, 2, 3, 4, 26, they will stay 26 for the duration of the study. It is kind of a natural assumption. And anyway, actually, in my results, I am not trying to estimate f, but estimation of f to a certain extent, if you have the values of the function, then estimation, denoised values of the function, then estimation of a function is basically, as far as statistics is concerned, is very traditional and relatively trivial task. So now, what I meant by the existing results, existing theoretical results on estimation and the statistic block model, they are relatively new. So there is a paper by Gao, Lu, and Zhou. It appeared in Annals of Statistics in 2015. So they are estimating lambda in the stochastic block model. And this is the rate of convergence. It is minimax, so meaning that the upper bounds and the lower bounds are the same up to a constant. They assume that they know the number of blocks in this paper. Later, Gao, he extended these results to a known number of blocks by using something like cross-validation, whatever. It is slightly different. And here, there is important part that there are two parts of this error. So you have m squared over n squared is the non-parametric error, because you have the order of m squared parameters, and I denote it by m capital because later on I will be dealing with this m capital all the time, just because this is the number of unknown probabilities, and here it is, and n squared is we dividing by the number of elements. And log m over n is actually the clustering error. And what it is just the log of the cardinality of the set of clustering matrices. So your clustering matrices, the cardinality is, you have log of m to the power n. You have m classes, class choices for each of the nodes, yes.
Lambda is these are the Bernoulli probabilities?
Yes, yes. We are looking at, I'm looking at this problem in Bernoulli setup, but technically everything that I am doing here for Bernoulli can be repeated for the, say, Gaussian, or actually anything, any random variable which is sub-Gaussian, and if you have sub-exponential, you will just slightly different convergence rate.
That's fine, yeah, but what does it mean for that to be sparse then?
This is, okay, here I'm talking about not sparse.
Well, what is, okay,
so I will talk about sparse here. So this is not sparse. Now, Klop, Tsebakov, and Verzelen, they extended it to the sparse case. So what they assume that all components of your matrix of probabilities are bounded above by rho n. This is what sparse means. So there,
And rho n is tending to 0.
yeah, and rho n is tending to 0, of course. Otherwise, there is no point putting n. So rho n, of course, it is some small number. So all probabilities are basically going to 0 at some rate, which depends on the size of the network. And this is their upper bounds for the matrix lambda. So the difference here that you have this rho n in front. And they did not, they assumed that m is known, so they need m to be known, and they need to basically either rho n to be known, or they need a balanced model. So all their clusters should be pretty much the same size, and there should be certain number of them. So this is the, and I think their paper either just was published or going to be published in a few months. I know that it is accepted. Now the static graphon, so in Gao, Lo, and Zhou, they assume that f belongs to a Holder class with the smoothness parameter alpha. Alpha is known, and this is the convergence rates. So you basically don't get any benefits if your function is very, very smooth, because since you have log n over n here, if your alpha is greater than 1, your clustering error will be overpowered, overpower your non-parametric error, and you would not get any benefits from the smoothness of the graphon. Now, Klop and Tsebakov and Verzelen have so they did this problem too. In the case of the graphon, they have lower bounds and the upper bounds. I did not present the formulas here because they are rather involved, and I mean, there is no benefit for you to see the formulas, but they have also matching kind of upper and lower bounds. And these are actually, the methodology everywhere is just basically the maximum likelihood. You do not the maximum likelihood, basically you have the least squares, that's what I meant. Yes, sorry, the least squares, you're completely correct, I'm sorry. And the only non-combinatorial, so these are combinatorial algorithms, and the only non-combinatorial distance-based estimation of the graphon is in a recent paper of Zhang, Levin, and Zhu, but their convergence rates are log n over n to the power 1/2, and they're kind of asymptotic. They don't have non-asymptotic bounds.
So what do you mean by non-combinatorial?
Non-combinatorial meaning something that is not NP-hard. Something that, so all these methodologies, and unfortunately my methodology too, I am talking about method of kind of, you need to do, you can do it, but then your rates are not guaranteed. So the rates are for ideal combinatorial case, but of course it can be relaxed and implemented, but then the rates will not be guaranteed.
Excuse me?
So what, yes?
Can you go back?
Yes.
So when you're doing non-parametric estimation of function, I can see the sense in making a holder assumption, because I can look at the data and maybe make an assessment.
This is actually results of Gao, Law, and Zhou, and I will tell you exactly what assumptions I'm making. This is just what people do. These results are not mine. All these results.
I understand that, but I mean, insofar as
yeah, these are not the sparse case. So this is the dense case. This is the sparse case. So this is the case where there are no restrictions on lambda, and this is the case when your maximum of lambda is less or equal than rho n. And actually, all results here, both this and this, are non-asymptotic. So technically, I mean, you can put. They did not put the constants, but you can make these results basically non-asymptotic. And particularly in what I'm going to show, you will see the constants. So I did not do any asymptotic. So nothing goes to anywhere. N does not go to infinity. L does not go to infinity. M does not go to infinity. Nothing goes anywhere. I mean, you have just fixed numbers and some constants. Some constants are ugly. I'm not going to show them to you. But actually, majority of in the upper bounds, actually, you will see the constants. In the lower bounds, you actually don't probably want to see the constants.
So are you going to make a holder assumption?
Okay, why don't we get a little bit into the talk, and you will see what I'm going to do. How about this? Will this work? Okay. So what I'm going to initially, I'm making very few assumptions. So we have at every time instant we have a collection of clustering matrices M of Mn. So what is a clustering matrix? It is a matrix of the size n times m, and so each row has exactly 1, 1, and the rest are zeros. So this is what the clustering matrix is, nothing else. So and the no xjk belongs is equal to 1 if node xik is equal to 1 if node I belongs to class omega k, and 0 otherwise. This is what clustering matrix is, nothing else. And the data, I assume that it is Bernoulli. As I said, you can do it with some other data, but since I need some specific results, in my case it is Bernoulli. And as I said, it is symmetric. You have 0 on the diagonal, and they're independent for different time instances. So now what is the model? At each point time L, and so far no assumptions, you have the clustering matrix. So your matrix of probabilities can be written in this form. This is very well known that if you have stochastic block model, this is kind of the representation of your probability matrix. You can think of it as doubly stochastic regression, where you have two matrices on two sides, and it is very inconvenient. And the only thing I assume that ZL belongs to the set of clustering matrices. So now what I'm going to do, I'm going to go from this inconvenient representation. This is a tensor. When you look at it at every point of time L, it is a tensor. It is not very convenient to work with tensors because we actually know how to work with matrices much better than working with tensors. So what I will try to do, I will try to get rid of tensors and get it into the setup in which we are I am as a statistician feel like I have firm ground. So what I am going to do, I am going to take each of these, at each time L, I am going to vectorize my matrix. I will get a lone vector, right? And I will vectorize the adjacency matrix B. So lambda is the true matrix, B is its observed version, and G is this vector matrix of probabilities at time L. So I vectorize all of them, and now if you just look at the results on Kronecker product, I will get this. This vector lambda at each time L will be equal to this matrix times GL. L from 1 to L. Now BJL now are Bernoulli from 1 to n squared, but now they are not independent because we have 0 on the diagonal and the matrix is symmetric. Now when I am going to do the least squares, it will be a drag because I will need to keep track of it. So why not getting rid of it? So now this is my matrix. So this is the case when n is 4 and m is 2. This is my clustering matrix. This is my matrix G, just for the first time point. And this is another clustering matrix. And here, this blue are actually the only elements that matter, right? Because on the diagonal I have 0, and above the diagonal I have the same elements. I don't need them. I don't want them, right? So let's get rid of them. Why keeping them? So let's remove these redundant entries, and to see what will happen, I'm using double indexing because otherwise it's hard to explain what I'm doing. So if you have index I1, I2 from 1 to n, you remove all the rows which correspond to I1 less or equal to I2. So now my BL becomes AL, and that's why I didn't use AL. So AL is kind of this adjacency matrix where the redundant elements are removed, and it is strand for every time point. And I remove also redundant elements from this matrix. And if you actually look carefully, after removing them, I'm removing some rows from the clustering matrix. And when I'm removing some rows, nothing happens to it. It still has 1 per row. So my new matrix C tilde L is still a clustering matrix. It's just a bigger clustering matrix, but it is a clustering matrix. It has all properties of the clustering matrix. Okay. So now we have these matrices. So each of them, this is my new data. And the beauty of it is that all of these elements now are independent. Nothing is dependent. Everything is independent here. No, but you still have a problem, because if you go back and you think of the matrix of probabilities of the blocks, it is a symmetric matrix still. So the probability of connection of group 1 and 2 is the same as probability of connection of group 2 and 1. So it would be desirable to remove this too, so you can do it too. So you, in order to remove the elements, basically these redundant elements in G, you again can use double indexing and get a new matrix which will be a sum of the elements of two matrices, and you take a sum only if it is not the probability of being in the same class, because then you don't need to add. And then your new model becomes very nice. So my new model is, I'm trying to recover theta L at each point L, and it is CL times QL. QL is G without the redundancy. So I don't need to keep track of anything, and and I have independent Bernoulli observations on each of the elements of the vector. And here is the silver lining. When you add these two matrices, since you can have only 1 per row, when you add them, you still have only 1 per row, because you cannot have 1 here and 1 here. So it is still a clustering matrix. So really your model now is like this. At every point L, you want to find theta, you need to find theta, which is the product of these two, and you have Bernoulli data on it. So this is the picture. So this is your vector of data. Now this will be your C tilde L multiplied by G. You can see that this element is redundant, so I can add the columns here, and when I'm adding the columns, you still have only 1, because, and this is your final representation. So this is what it is. So now we have it at every point L. So now let us do the final vectorization. So now I can stack these columns into the matrices, and I will have matrix A with columns AL, matrix theta with columns theta L, and here I should have, of course, put 0, 1, whatever, because your theta is between 0, 1, not R. This is just a typo. But I mean, if you have Gaussian data, you will have just the same structure, so you can do the same thing. The fact that I'm working with Bernoulli is completely incidental to this technique. And then you have Q, which is non-redundant vector of probabilities, or whatever weights you have in your matrix that you want to recover. And so this is one thing, so you can write it in a matrix form, or you can vectorize matrix A further, and you will get then theta, which is the vectorized version, which is just basically taking all these thetas stack on the top of each other. And then you have two versions of the final model. You can have A capital is equal to theta plus psi, or you can have it A is equal to theta plus psi, where theta is in this form. And I will show what C should be. I don't know, where is it? Let me check. Yeah, here. So where matrix C is basically just the block diagonal matrix of these clustering matrices. And you have I are independent Bernoulli variables. So now every basically statistician looking at it will say, this is, I mean, a standard structure. If I use C, it is just regression with independent Bernoulli variables. And if you don't have Bernoulli, you have Gaussian, you have, if you have weights and you have Gaussian measurements on them, or you take the, say, energy levels, then it will be chi-squared. You will have basically regression with some independent errors, whatever your model is, because factorization has absolutely nothing to do with the fact that they are Bernoulli. So this kind of can be used for other purposes. So now this is the final picture. You get these matrices, you string them, you get these elements, you represent each of them like this, and then at each time point you have this vector which is a clustering matrix times the unknown probabilities, and then you can string them into the vector, and this is what you obtain. So this is basically all the picture of the methodology. So now we are going to look at what do we do statistically. So now your vector, if you look at this matrix Q, this matrix, the rows of this matrix, we can consider them to be either smooth or at least have some structure. So what I assume that there is some orthogonal basis in which these rows of this matrix have sparse representation. So if your probabilities are indeed smooth, you can use Fourier. If you assume that you may have some jumps, you can use wavelets. It does not matter, it's just basically whatever structure you assume. So as I said, Fourier or wavelets will both work. And here is the beauty of it, that when so what does it mean? It means that H times Q transpose, because I'm working with the rows of Q, is sparse, so it has, I need a small number of coefficients to represent my vector, my matrix. And now when I factorize it, again with Kronecker product, I get this, and matrix H Kronecker IM is actually an orthogonal matrix again. So now I'm looking for the vector of coefficients, which is represented as WQ, and this vector of coefficients is, has only few non-zero components. So where is sparseness coming from here? It's coming from two things. First, that my probabilities are smooth in time. So at each time point, I don't need all coefficients. I need only few. Number two, I may have some probabilities that are identically equal to 0, and then I don't, or they can be constant, then I have one coefficient, or they are identically equal to 0. So I cannot recover sparseness in the Klopp and Tsibakov sense, but I can have a network where some probabilities are large and the others are identically equal to 0. They are not rho n, they are not n to the power minus 5. They just 0. I mean, these people, they never met each other, they have no business with each other, and we can basically, for every practical purpose, assume that they have 0 probability of connection. And what basically it means now that cardinality J of set J is small. After that, it is kind of, you need to account for the clustering matrices because I want my technique to be adaptive. So I assume that I have a set of clustering matrices which is a subset of all possible clustering matrices. What this set is, I'm not making any assumptions, but I assume that I kind of know how my clustering may change in time. And then you get just penalized least squares. So you're recovering the number of blocks, you're recovering the locations of non-zero coefficients, you're recovering the coefficients themselves, and the clustering matrix as the minimum of this. And this is the penalty. Now notice that in the penalty nothing goes anywhere. The penalty has exact coefficients, 11 and 11 over 2, which come actually from Bernoulli. If you have different variables, different errors, you will have different coefficients here. The beauty of it is here, J is the number of coefficients you need to estimate, log is logarithmic factor, because you need to find those coefficients among m squared L, right? So this is the logarithmic factor you cannot remove. And this is the logarithm of the cardinality of the set of clustering matrices that you assumed. So you can handle any set of clustering matrices, it does not matter. And then the algorithm, you need to solve optimization problem, of course, for solving it practically you need convex relaxation. You solve it for every value m, then you check without the penalty, because for every m you're dealing only with the least squares. You run it with penalties, you have only basically a finite number of elements, and then basically you recover your vector, pack it back into the tensor using the symmetries.
Where does the 11 come from?
It comes from the exponential inequalities for Bernoulli random variable. Because our errors are Bernoulli, so when you're applying basically this probability inequalities, I mean exponential type inequalities, there are constants. So for Bernoulli, as far as I remember, it is either 2 or 4, and then you have to double something. So if you say working with Gaussian distribution or any other distribution, with Gaussian your constant will change. If you have sub-exponential random variables, you again will have slightly different logarithmic factor here, I believe. Okay, now what I obtain as a result is an oracle inequality. So I wrote it in probability. Why? Because the lower bounds will be in probability, but you have very similar result in expectation. Notice you have exact constants in the upper bound everywhere, so you can plug in your favorite n and L and m. And what you have here, you have basically penalty, and this is a very small factor. And if you want this to hold with this probability, then this will be your t. And obviously, since exponential function decreasing very fast, this additional factor is very, very small. So really, you recover it up to the... And this is basically how well you can represent your tensor using just j coefficients. So it is a trade-off. And here, as you noticed, I did not put any assumptions on smoothness of what I am doing, any orthogonal transform, any number of coefficients. If you chose wrongly, you will have large j. If you chose correctly, you will have j small and very good error. And here, this is obviously the clustering error, logarithm of the cardinality, and this is the non-parametric error. Now you cannot, of course, do lower bounds for the completely general case. So for the lower bounds, I assumed that we have at most n not nodes that can change their memberships from one time instant to another. Just as an example, you can do it with something else, because for this set I can easily calculate the cardinality, and then you get the upper bounds. So this is non-parametric error, this is initial clustering error, this is a clustering error due to the changes. And then you can actually get the matching lower bounds. So for upper bounds, as you noticed, I did not have any assumptions. For lower bounds, I need some assumptions. They are not drastic, like n is greater than 2m, l is greater than 2, and you need to have the number of elements which is greater or equal than some fixed gamma times m squared. Otherwise, I run into the problem. Actually, the main problem here is that when you are reconstructing Fourier, you need to have probability, so everything should be non-negative. This is actually where all restrictions in the lower bounds come from. So they are more technical than conceptual. And then you get the lower bounds for the error with just some constant c depending on this gamma, which is the number of elements that you need to, basically the cardinality of the set J. Now you, for DSBM, the estimate, as I said, is adaptive with respect to the unknown number of classes. You need to assume some complexity of the set of clustering matrices. There are no probabilistic assumptions on the mechanism that generating these changes in the membership. On the other hand, if you have a mechanism, you can calculate the size of this set of clustering matrices that happens with a high probability and then apply there. And then you will know what penalty to put. If L is equal to 1, that you don't need any H, but you can automatically obtain an adaptive estimator for a sparse SBM. But it will be, as I said, sparse in a different sense. So you would not have uniformly small probabilities. Some probabilities can be large, they can be close to 1, but there can be lots of zeros. Any number of zeros you want, because you just naturally would not estimate these entries. If they are 0, they are 0. They will be 0. And you can handle the situation when the number of nodes changes in time. And this case, you can have denote by n the maximum number of nodes and create the class with no interaction with the others. So if you are out of the network, you're in the network, but you don't have interaction. So this will be another class, and then you can handle this situation. Now I guess I have only 3 more minutes, right? So I'm running out of time, so I probably will skip the estimation of the graphon almost. I will just show you the assumptions. So my assumptions here is that the assumptions are just on coefficients in this transformation, orthogonal transformation. So I don't assume that the function is spatially smooth, but it is only piecewise spatially smooth. So really, I can handle 2 regimes. One regime is when this new 1 is equal to infinity, and then you have the basically dynamic stochastic block model. Everything is constant, but you have any number of jumps, even infinite number of jumps. Your kn can depend on n. Or you have piecewise smooth graphon, because when we are talking about piecewise smooth function, we are talking about finite number of jumps, not infinite number. So this is these are the 2 situations that are considered. The estimation algorithm, and you have the upper bounds. Minimum here is due to the situation that if L is large, you're better off doing the transform. If L is small, you're better off skipping the transform, and this is your non-parametric rate. And similar situation for the smooth graphon. And so this is the contribution. So what this talk does, it basically, what I'm trying to sell here is this penalized least squared optimization algorithm. It can be actually used for other types of errors. You don't need to have Bernoulli. You can have other errors. I did not put any assumptions on the mechanism generating changes. If you want some other changes in the memberships, not at most and not, you will just need to calculate the complexity of the set of your clustering matrix and take the logarithm of it. You don't need to knowledge of the number of classes. You get the oracle inequalities. It is non-asymptotic. Nothing goes to infinity. It allows, as I said, variety of extensions. And vectorization of the model actually leads, I believe, will lead both to faster computing, and it leads to infinitely simpler mathematics than in the previous works that I cited. Like mathematics in my papers, I mean, all the proofs are so much easier just because you have basically a standard regression model in the nutshell. Now, of course, there are shortcomings, which I already mentioned. Sorry, not maximum likelihoods. The least squares estimation that I presented is NP-hard. So in the form in which it is written, it is not computationally viable, but I believe that it can be relaxed to be computationally viable by some EM algorithm or some two-step algorithm. Of course, in this case, you don't guarantee the rates, but it is always good to know at least some golden standards and what penalty to put, if nothing else. And another, of course, shortcoming is that it would be nice to generalize the dynamic graphon to the case when your variables depend on t. And some problems are hard to solve, so this problem was hard to solve for me at the moment. And actually, some problems are always hard to solve. Guess what is the title of this painting? Nobody can guess. Okay, and thank you very much.
Questions?
Yeah. Yes.
I think one can generalize this to also if you have some dependence structure. I mean, one could think of that one has in the background a time series and that you observe it at discrete.
If you have a time series, you can still generalize it. You will just, instead of having the standard regression with independent components, you will have dependency in your covariance matrix, whatever, and then you again probably can use this least squares, just you will need to use your assumptions to tweak the model, of course. Because vectorization has nothing to do with actually with any assumptions except the fact that we have basically the diagonal is non-informative and all my matrices are symmetric, and that clustering matrices have zeros and ones. So the main basically technique before the results has nothing to do with any assumptions. So I'm sure you can use it for something else. And this is actually the main part of my talk, is that it is a very useful tool with which you can obtain both theoretical results, and I believe it may be useful for computations.
So normally in penalizer regression, you have a problem with selecting this penalty parameter.
Yes, but here I know the errors, so I don't, my errors, think about this, it is Bernoulli, where the penalty parameter comes from, that you have, say, Gaussian noise and you don't know sigma. Here it's Bernoulli, there is nothing else. The mean, the variance is bounded. So it is higher than necessary. And this is actually the problem if you have uniformly small probabilities. The uniformly small probabilities. You will have rho n, this sparsity parameter, in front of your penalty. And I did not extend it to the sparse case, only for this reason. If you put rho n in front of this penalty, with maybe slightly different constant, I don't remember, you will get the same result when you have uniformly small probabilities bounded by rho n. But I don't know how to adaptively choose it. And I wanted to have kind of, for this paper, to have a clean result. But it is basically it is very easily extendable. You just need to have exactly this rho n in front. So before your penalty. And then you will have the same result for the sparse network in the sense of uniform boundedness of probability by some small number.
What if your function, so if in this sparse setting you would make the function only square integrable and not bounded?
If your function is f is not bounded, obviously if the function is not bounded, it will not be Bernoulli, right? You cannot, if you are...
No, but if you put a row in front, then you can most of the time it will look bounded, but...
you know, it is a good question. I believe that it will require additional analysis because you need to write the model completely and see what the penalty should be. But vectorization and stringing it will work just the same no matter what actually your model on your data is and what your model on the underlying parameters are, as long as you have this pairing and you have the clustering. Because it is the initial part of the stock actually has nothing to do with Bernoulli, with boundedness, because what I'm using is just purely algebraic techniques. I take the product of three matrices, use vectorization, write it with Kronecker, then string it and write it with another Kronecker, and then get basically the standard model matrix times vector. And if my vector is coming from the matrix which has rows that have some structure, I can apply some transform on the right and rewrite it again as a new matrix times the vector of coefficients. That's all. So it has the initial part of the stock has absolutely nothing to do with any model as such. It has something to do only with the algebraic formulation of the stochastic block model, whether it is in time or not. And it can be used actually without time. You just will have vectors and you will not have matrices that you need to string. And of course you will not have this orthogonal transform on the right. But it still can be a strange. So if you have doubly stochastic regression, really, you don't need to do doubly stochastic regression. You can do just usual stochastic regression. There is no problem where the matrix is on the left and on the right. This is the first take out message. The matrix on the left and on the right can be made only into the matrix on the left, and forget about the right.
Okay, maybe last question from Harry.
I'm not sure what it means to talk about a sparse setting, and you're also saying that nothing goes anywhere, right? So
what I mean, okay, sparse setting can be, there are two kinds of sparsenesses that can be handled. So the first kind of sparseness is the type of sparseness that Jennifer and Christian were talking about. So it is asymptotic kind of sparseness. When the size of the network is growing, your probability, the maximum probability of connection is bounded by rho n, where rho n goes to 0 at some rate. So this is one kind of sparseness. And of course it is asymptotic, but if you have n finite, say, you can assume that it is less, that your maximum probability of connection is less equal than rho n, and formulate your results in terms of n and rho n. I mean, if your n is growing and you know what your rho n is, you will find exact bounds. But they are non-asymptotic. For every n and every dependency rho n, you can calculate it. This is what I mean by nothing goes anywhere. Because as a statistician, n is always a number. So, you know, I saw papers where there was square root of log n divided by 7. I figured out in order it is positive, the penalty is not 0, you have n more than 1 million, and there are no sample sizes like this. So this is what I mean by non-asymptotic. Everything can be calculated. All the bounds are exact. So this is one kind of sparsity. The other kind of sparsity, you can consider a network, dynamic or non-dynamic, where there are groups that just have 0 probability of connect. So you don't have very small probabilities. You have either normal probabilities, say probability of 1/10 for some group, I mean, and then you have probability 0 between many groups, because if we are considering, say, the whole of university, there are some students of university that are in groups that we, for every practical purpose, can assume to be 0, or different cities or whatever. So this is another kind of sparsity which may work in some other models, like epidemic models. If there is absolutely no connection between something and something, you can, for every practical purpose, assume this probability to be 0.
Okay, I think we'll just give it right here. Maybe if there are more questions, then ask during the break, which is now. So let's thank the speaker again.